Hi and hello. Welcome to the ARM Basics for Hackers course. So this is a very short course on the very basic instruction set of ARM. So you can just take this course if you want to learn about some basics about ARM. So this will help you if you want to do further binary exploitation or reverse engineering in the ARM platform. So it will also help you if you want to go through any further mobile exploitation or something like that. So about the requirements, you only require a PC. So you don't also require a PC, but if you want to do it by yourself, you should require a PC or anything. So you can also do it in a mobile too, but I don't think that is not very practical. So this course is very useful for hackers, and if you want to know about assembly instructions, so especially ARM assembly instructions, you can take this course, and this will be useful for anyone you want to move to ARM exploitation or something like that, and it can be also taken by mobile pen testers. So this is a very short course, and you can also take this course, which is also mine, and this covers all the content which I brought you in this course. So this is pretty much the same, but this have more advanced topics like reverse engineering by and format string vulnerability, buffer overflow, and etc. So you can take this course if you want to. So the pricing will be different on these courses. Okay, so we will move on to our course in the next video. Okay, bye. So in this video we'll be looking at the lab setup. So this lab setup is not very important, but if you want to try it on yourself, you can just go on and download these labs and try these code examples by yourself. Okay, so you have to just Google for Asiria Labs, and this is the VM. So this is the VM, and you can just download this by yourself, and this is the link, so you can download this. So if you don't have any space or something like that, you can just manually emulate this using Kemu. So there is also a tutorial right here. So but this thing is kind of little complicated, but I always prefer this VM. So you can just download this by your link. After downloading this, you can just unzip it. It's a zip file. You can just use it by WinRAR or anything else. So and after extracting that, you will get this file. I will go to this folder, and so you will get these files. So if you look at here, there is a VMX, which is a VMware virtual machine configuration file. You can just double click on this and it will take you to the VMware. Okay, so you can just press on run, and that's it for the installation. You can just press here. Okay, okay, so you can just click on here to turn on the lab. So that's all for the installation. So bye. So what is ARM? ARM, which is also known as advanced risk machines, is a family of reduced instruction set computing architectures for computer processors. Like the Intel x86 or x64, ARM is also an architecture which comes under RISC. Okay, and ARM processors are mainly used in these electronic devices which require small energy. So smartphones, tablets, and other mobile devices uses ARM processors because ARM consumes very less energy compared to our CISC architecture processors. Okay, and because of the small sizes, they require only few transistors, which enables them to use very small energy. Okay, And so if you want to go and look about more about it, you can go to this website. And ARM has more registers than the CISC processors. So the concept behind the ARM is, if they have more registers, so they have more registers than the CISC. So since ARM has more registers than the CISC processors, it will help them to execute tasks very quickly than the CISC processors. So this is the core concept behind the ARM. And also in this ARM processors, instructions can be either be 2 or 4 bytes. In the thumb mode, the instruction is in 2 bytes, and in the ARM mode, the instruction is in the 4 bytes. So they have a fixed size in their instruction, and these are the different versions of our ARM. In this course, we'll be looking on the vulnerabilities in ARM 6. Okay, so these are the different ARM architectures released in all those years. And if you want to get that, you can just Google it in the Wikipedia. This is from the Wikipedia. And these are the different families of ARM architectures, and we'll be looking at ARM 11 family, okay, which has the ARM 6 architecture. And I actually missed something. Let me just go back. So if you look here, until this ARM Cortex R52, they are using 32-bit as the width. So after that, in the ARM Cortex R82, they are using 64-bit as the width. Okay, and you can get the other versions if you use Wikipedia, and this is also copied from Wikipedia. And the important thing in ARM is it has two states. Okay, one is ARM mode and another is the thumb mode. So these states has nothing to do with privilege levels, but it differs in the instruction. Okay, so the thumb state, the instruction works in 16-bit, but in ARM state instruction works in 32-bit. So we will see that what is the difference when we do a buffer overflow. Okay, hi and hello, welcome to the ARM basics for hackers course. So this is a very short course on the very basic instruction set of ARM. So you can just take this course if you want to learn about some basics about ARM. So this will help you if you want to do further binary exploitation or reverse engineering in the ARM platform. So it will also help you if you want to go through any further mobile exploitation or something like that. So about the requirements, you really require a PC. So you don't also require a PC, but if you want to do it by yourself, you should require a PC or anything. So you can also do it in a mobile too, but I don't think that is not very practical. So this course is very useful for hackers, and if you want to know about assembly instructions, so especially ARM assembly instructions, you can take this course, and this will be useful for anyone you want to move to ARM exploitation or something like that, and it can be also taken by mobile pen testers. So this is a very short course, and you can also take this course, which is also mine, and this covers all the content which I brought you in this course. So this is pretty much the same, but this have more advanced topics like reverse engineering by and format string vulnerability, buffer overflow, and etc. So you can take this course if you want to. So the pricing will be different on these courses. Okay, so we will move on to our course in the next video. Okay, bye. ഓക്കെ, ലാസ്റ്റ് വീഡിയോ പറഞ്ഞ പോലെ നമുക്ക് കുറച്ച് ബേസിക് ആയിട്ടുള്ള അസംബ്ലിയുടെ കുറച്ച് പാർട്ട് വേണം. സോ ആദ്യമേ തന്നെ നമുക്ക് മൂവ് ഇൻസ്ട്രക്ഷനിൽ നിന്ന് തുടങ്ങാം. മൂവ് ഇൻസ്ട്രക്ഷൻ എന്ന് പറഞ്ഞാൽ പ്രത്യേകിച്ചൊന്നുമില്ല, ഡാറ്റ മൂവ്മെന്റിന് വേണ്ടിയാണ് യൂസ് ചെയ്യുന്നത്. ഡാറ്റ മൂവ്മെന്റ് എന്ന് പറഞ്ഞാൽ വാല്യൂ കോപ്പി ചെയ്യാൻ. ഫോർ എക്സാമ്പിൾ നമ്മുടെ സിയിലും കണ്ട വേറെ ലാംഗ്വേജസിലൊക്കെ ഇൻഡ് ഐ ഈക്വൽ ടു 5 എന്ന് പറഞ്ഞാൽ എന്താണ്? 5 എന്ന് പറയുന്ന വാല്യൂ ഐ എന്ന് പറയുന്ന വേരിയബിൾ അസൈൻ ആവുന്നില്ലേ? അതേപോലെ തന്നെ ഇവിടെ നമുക്ക് റിലേറ്റ് ചെയ്യാം. എന്ന് പറഞ്ഞാൽ മൂവ് ഡെസ്റ്റിനേഷൻ കോമ സോഴ്സ്, ഇവിടെ ആയിരിക്കും സോഴ്സ്, ഇവിടെ ആയിരിക്കും അതിന്റെ ഡെസ്റ്റിനേഷൻ. ഇതിപ്പോ എന്ത് വേണമെങ്കിലും ആവാം. ഇപ്പൊ ഇവിടെ കണ്ടോ, വാല്യൂ 1 എന്ന് പറയുന്ന വാല്യൂ ഇ എക്സിലോട്ട് പാസ് ചെയ്യുന്നു, കോപ്പി ആവുന്നു. അതേപോലെ ഇ ബി എക്സ് ബ്രാക്കറ്റ് കിടക്കുന്നതെന്ന് പറഞ്ഞാൽ ഒന്നുമില്ല, ഈ ഇ ബി എക്സ് പോയിന്റ് ചെയ്യുന്ന മെമ്മറി ലൊക്കേഷനിലുള്ള വാല്യൂ ആയിരിക്കും ഇ എക്സിലോട്ട് പാസ് ചെയ്യുന്നത്, ഇ എക്സിലോട്ട് കോപ്പി ആവുന്നത്. അപ്പം ഇതാണ് ഡെസ്റ്റിനേഷൻ, ഇതാണ് സോഴ്സ്. അപ്പം ഈ ഇൻസ്ട്രക്ഷൻ എക്സിക്യൂട്ട് ആകുമ്പോൾ 1 എന്ന് പറയുന്ന വാല്യൂ ഇ എക്സിൽ കയറും. ഇതിപ്പോ എക്സിക്യൂട്ട് ആകുമ്പോൾ ഫോർ എക്സാമ്പിൾ ഇ ബി എക്സ് പോയിന്റ് ചെയ്യുന്ന മെമ്മറി ലൊക്കേഷനിലുള്ള വാല്യൂ 5 ആണെന്ന് വിചാരിച്ചു, ആ 5 ഇതിനകത്തോട്ട് കോപ്പി ആവും. ഇത്രയേ ഉള്ളൂ മൂവ് ഇൻസ്ട്രക്ഷൻ. നമുക്ക് ജി ഡി ബിയിൽ അതൊന്ന് ഡീബഗ് ചെയ്ത് കാണിക്കാം, നമുക്ക് കുറച്ചും കൂടെ ഒരു ഗ്രാഫ് കിട്ടും. വേണ്ട, ഞാൻ ഇവിടെ എല്ലാം കൊടുത്തിട്ടുണ്ട്. ജി ഡി ബി ഒന്നുമില്ല, ഡിഫാൾട്ട് ഈ ലിനക്സിന്റെ കൂടെ വരുന്ന ഡീബഗർ ആണ്. കോഴ്സിന്റെ സ്കോപ്പിൽ ഇല്ല അത്, എന്നാലും നമുക്ക് ഈ പറയുന്ന ഇൻസ്ട്രക്ഷൻസ് മനസ്സിലാവാൻ ഈസി ആവും, അതിന് ഇൻക്ലൂഡ് ചെയ്തതാണ്. ഓക്കെ, കണ്ട ഇവിടെ കാണാം നമ്മുടെ മൂവ് ഇൻസ്ട്രക്ഷൻസ്. ഇ ബി എക്സിലേക്ക് 4 അസൈൻ ചെയ്യുന്നു. അങ്ങനെ ഇത് ഹെക്സ് ആണ്, ഇതെല്ലാം എക്സ് വരുന്നത് ഹെക്സ് ആണ്. അപ്പം ഇത് നമുക്ക് കാണാം എങ്ങനെ ഈ വാല്യൂ കയറുന്നത്. സോ ആദ്യമേ തന്നെ ഒരു ബ്രേക്ക് പോയിന്റ് കൊടുക്കാം. ബ്രേക്ക് പോയിന്റ് ഒന്നുമില്ല, നമ്മൾ കൊടുക്കുന്ന ബ്രേക്ക് പോയിന്റ് എന്തിനാന്ന് വെച്ചാൽ ഈ പറയുന്ന പ്രോഗ്രാമിന്റെ ലൈൻ ബൈ ലൈൻ എക്സിക്യൂഷൻ അല്ലേ ഇവിടെ നടക്കുന്നത്. അപ്പൊ ഏതെങ്കിലും ഒരു ലൈനിലോ എവിടെയെങ്കിലും ഒരു പർട്ടിക്കുലർ ഇൻസ്ട്രക്ഷനിലോ ബ്രേക്ക് കൊടുത്ത് അവിടെ പോസ് ആവും. ഈ പോസ് ചെയ്യുന്നത് എന്തിനാന്ന് വെച്ചാൽ നമുക്ക് ഈ പറയുന്ന വാല്യൂസ്, പറയുന്ന രജിസ്റ്റർ വാല്യൂസ് ഇൻസ്പെക്ട് ചെയ്യാനോ അല്ലെങ്കിൽ കോഡ് ഇൻസ്പെക്ട് ചെയ്യാനോ എന്തിനെങ്കിലും ആയിരിക്കും. അപ്പം ബ്രേക്ക് പോയിന്റ് കൊടുത്തില്ലെങ്കിൽ എന്താ സംഭവിക്കുന്നതെന്ന് അറിയാം, ഇതങ്ങ് റണ്ണായി പോകും, വേറെ ഒന്നും വരത്തില്ലല്ലോ. നമുക്ക് ഈ ഓരോ ഇൻസ്ട്രക്ഷൻ ഇതിനകത്ത് എങ്ങനെ കയറണമെന്നുള്ളതല്ലേ കാണേണ്ടത്. അപ്പൊ ഞാൻ സ്റ്റാർട്ടിൽ ബ്രേക്ക് കൊടുത്തു. ഇവിടെ സ്റ്റാർട്ടിലാണ് നമ്മൾ അസംബ്ലി കോഡ് എഴുതി തുടങ്ങുന്നത്, സ്റ്റാർട്ട് എന്ന് പറയുന്ന സെക്ഷനിൽ. അതിന് ഈ ബ്രേക്ക് അണ്ടർസ്കോർ സ്റ്റാർട്ട് വന്നിട്ടത്. ഓക്കെ, ഇനി റൺ ചെയ്യാം. അന്നേരം 6 കൊടുത്താൽ മതി. ഫസ്റ്റ് മൂവ് ഇ ബി എക്സ് 4. അപ്പൊ 4 എന്ന് പറയാൻ ഞാൻ പറഞ്ഞു സോഴ്സ് ആണ്, ഇ ബി എക്സ് ആണ് ഡെസ്റ്റിനേഷൻ. അപ്പൊ ഈ ഇൻസ്ട്രക്ഷൻ എക്സിക്യൂട്ട് ആയി കഴിയുമ്പോൾ ലൈൻ ഇവിടെ ആരോ കാണിക്കുന്നുണ്ടോ. അപ്പം ഇതെന്താ ഉദ്ദേശിക്കുന്നതെന്ന് പറഞ്ഞാൽ ഈ ലൈനെ ഇനി എക്സിക്യൂട്ട് ആകാൻ പോകുന്നതെന്നുള്ളൂ. അപ്പോൾ 4 ഇ ബി എക്സിലോട്ട് കയറും. അതിന് നമ്മൾ ഓരോ പ്രാവശ്യം സ്റ്റെപ്പ് ചെയ്യണം എന്ന് പറഞ്ഞാൽ സ്റ്റെപ്പ് കൊടുത്താൽ ഈ ഇൻസ്ട്രക്ഷൻ എക്സിക്യൂട്ട് ആവും, പിന്നെ അടുത്തതിലോട്ട് വരും. ഇപ്പൊ അത് മൈൻഡ് ചെയ്യണ്ട, നിങ്ങൾ ഈ പറയുന്ന വാല്യൂ ഇരിക്കുന്ന മാത്രം മൈൻഡ് ചെയ്താൽ മതി. സോ ഞാൻ എസ് ഐ കൊടുത്തു. എസ് ഐ കൊടുത്തപ്പം അതാണ്ട് ഇ ബി എക്സ് 4 ആയി. 4 അല്ലായിരുന്നോ? അപ്പം ഇ ബി എക്സിലേക്ക് 4 ആയി. ഇനി അടുത്ത് നോക്ക്, ഇ എക്സ് ബി എന്ന് പറയുന്ന വാല്യൂ എന്താണെന്നറിയോ? 11 സത്യം പറഞ്ഞത്. ഇത് എക്സ് ചെയ്തിരിക്കുന്നതുകൊണ്ടാ ബി എന്ന് വരുന്നത്. അതും കൂടെ ഞാൻ സ്റ്റെപ്പ് ആയി കൊടുത്തു. കണ്ടോ എന്താ, ഇ എക്സ് ബി വന്നു, ബി 11. ഇനി അടുത്തത് ഇൻസ്ട്രക്ഷനും ആവാം. ഓക്കെ, ഇന്റർമീഡിയറ്റ് വാല്യൂ ആവാം, അതേപോലെ തന്നെ ഇൻക്രീറ്റ് വാല്യൂ ആവാം. അതേപോലെ തന്നെ നമുക്ക് രജിസ്റ്റേഴ്സിന്റെ വാല്യൂ ഇതേപോലെ കോപ്പി ചെയ്യാം. അപ്പൊ ഇതെന്താ സംഭവിക്കുന്നതെന്ന് പറഞ്ഞാൽ ഇ ബി എക്സിലെ വാല്യൂ ഉണ്ടോ 4, അത് ഇ സി എക്സിലോട്ട് കോപ്പി ആവും. ഇ സി എക്സ് ഇപ്പൊ 0 ആണ്, ഇ ബി എക്സ് 4. അപ്പൊ ഇത് എക്സിക്യൂട്ട് ആയി കഴിയുമ്പോൾ ഇവിടെ എന്താ സംഭവിക്കുന്നതെന്ന് നോക്കുക. ഒരു എൻ്റർ കൊടുത്താൽ എൻ്റർ കൊടുക്കുന്നത് എന്തിനാന്ന് വെച്ചാൽ നേരത്തെ ഒരു കമാൻഡിനകത്ത് എക്സിക്യൂട്ട് ചെയ്തിട്ടുണ്ടെങ്കിൽ എൻ്റർ അടിച്ചാൽ അത് വീണ്ടും റിപ്പീറ്റ്. ഓക്കെ, അപ്പം കണ്ടോ ഇ സി എക്സ് 4 ആയി. ഈ ഇൻസ്ട്രക്ഷൻ അല്ലായിരുന്നു എക്സിക്യൂട്ട് ആയത്. ഇത് കണ്ടോ ഗ്രേ ആയത്, ഇത് എക്സിക്യൂട്ട് ആയി കഴിഞ്ഞ് ഇനി എക്സിക്യൂട്ട് ആവാനുള്ളത് ഇതാണ്. അപ്പം അതാണ് സംഭവിച്ചത്, ഇ ബി എക്സിലെ വാല്യൂ ഇ സി എക്സിലോട്ട് പോയി. ഓക്കെ, അടുത്ത ഇ എസ് പിയിലെ വാല്യൂ ഇ ഡി എക്സിലോട്ട് പോവാണ്. അപ്പം സ്റ്റാക്കിന്റെ ടോപ്പ് നിൽക്കുന്ന വാല്യൂ എന്താണ്? ഇത് സ്റ്റാക്ക് ഒന്നും ഞാൻ എപ്പോഴേ പറഞ്ഞില്ല, എന്നാലും ഇങ്ങനെ ഒന്ന് ഐഡിയ വെച്ചാൽ മതി. ടോപ്പ് നിൽക്കുന്ന ഈ ഇ എസ് പി നടക്കുന്നുണ്ടോ, ESP സ്റ്റാക്ക് പോയിന്റർ ആണ് പോയിന്റ് ചെയ്യുന്നുണ്ടോ ടോപ്പ് 1 എന്നുള്ളത്. ഈ 1 EDX കയറും. EDX ഇപ്പൊ എത്ര 0 കണ്ടോ, EDX എന്താ 1 ആയി. ഇപ്പം ഈ സോർ എന്ന് പറഞ്ഞാൽ ഒന്നുമില്ല, 2 0 ആക്കാൻ വേണ്ടിയാ, ബാക്കി കുറച്ചും കൂടെ കാണിക്കാൻ വേണ്ടിയാ, അത് മൈൻഡ് ചെയ്യേണ്ട കേള്. ഓക്കെ, ഇവിടം തൊട്ട് ഞാൻ പറഞ്ഞ സബ് രജിസ്റ്റേഴ്സിലും കോപ്പി ചെയ്യാം. എന്ന് പറഞ്ഞാൽ എന്താണ്, TX-ന്റെ ലോവർ ബിറ്റ് കഴിഞ്ഞ വീഡിയോയിൽ പറഞ്ഞായിരുന്നു. ഇത് ഇതിന് സ്റ്റെപ്പ് ചെയ്യുമ്പോൾ കണ്ടോ, EX-ലെ ലോവർ ബിറ്റ് 3 വരും. ഇത് EX എന്നാണ് കാണിക്കുന്നത്, അതുകൊണ്ടാണ് ഈ പറയുന്ന 3 എന്ന് ഇവിടെ ഇങ്ങനെ വരുന്നത്. സത്യം പറഞ്ഞാൽ ഇത് ലോവർ എൻഡിലാണ് വരുന്നത്. അടുത്ത BX കണ്ടോ, അതിന്റെ ലോവർ ബിറ്റില് A വന്നു. ഇനി CL-നകത്തോട്ട് AL കോപ്പി ചെയ്യുകയാണ്. CL ഏതാ താണ്ടെ ഇവിടാണ്. ഇവിടെ നമ്മൾ എന്താണ് കോപ്പി ചെയ്യുന്നത്, AL-ലെ 3. ഇപ്പം ECX 3 വരും കണ്ടോ, 3 വന്നു. സോ ഇത്രയുള്ള മൂവ് ഇൻസ്ട്രക്ഷൻസ്. ഇതിന്റെ വേണമെങ്കിൽ ഞാൻ ഈ പറയുന്ന ചെയ്ത് പഠിക്കാനുള്ള ഇപ്പോൾ എഴുതിയ കോഡ് ഞാൻ അയച്ചുതരാം. In this video, we'll be looking at the add instruction. So as the name suggests, it is an arithmetic addition. So add instruction can add the values of two registers and also store that result into another register. So if you look at here, it says add destination comma source 1 and source 2. If it was a 2 register here, if I say this was like here R2 and R3, it will add the value in R2 and R3 and store it into R1. We can look at an example here. If it says R1 is 2 and R2 is 6 and R3 is 1, what happens here if we execute this instruction? It adds the value in R2 and R3. What is the value in R2? That is 6. And what is the value in R3? That is 1. It will add those values and will produce a result, that is 7. 6 plus 1 is equal to 7. And that 7 is stored into R1. So that is the destination, right? And these two are the sources. And it can also add an immediate value like this. It says add R1, R2 and 4. And what happens here is R2 will be added with the value 4. That is the value in R2, that will be 6 plus 4 equal to 10. And that value will be stored into R1. So I will again go into the lab. And we can do an exercise. If I just quit and I will do a program, and we can see where is the add. Yeah, if I just say cat add.s, so these are our add instruction. You don't have to mind this. This is used for properly exiting the program. Okay, we just have to see how this works. So firstly I will use tdb and say add, and it will take some time. Yeah, it's done. And if I do a discuss and say start, and I can see all the instructions. So you will put a breakpoint at the start like we did before, and we will run the program using R. And the program is now started. We can see all the registers contain the value of 0, and we are executing the first instruction that stores the value of 2 into R2. So I will do SI, and we can see 2 is stored into R1, and in the next instruction 8 will be stored into R3. You can see R3 contains 8, and the next instruction it says add the value of R1 and R3, that is 1 and 8, and store that result into R2. So 8 plus 2 is equal to 10. That will give a in hex. So if I do an SI, R2 will contain a value of a, that is 10. So if we look here, yeah, R2 contains a value of a, that is 10. 2 plus 8 is equal to 10, right? And the next instruction says that add the value in 5 plus 1, that is 5 contains 0, and add 1 to it. So 0 plus 1 is equal to 1, and that 1 will be stored into R1. So if I do a SI, R1 will contain a value of 1. And the next instruction says add and S. This like suffix, yeah, suffix can be also used in another instructions. So I talked about flags before. If I use S, and if the result has any like negative result or produces a 0, and these flags will be set. But if you don't use a S, if the instruction was simply just add, it will does not set the flag. If you use a S, it will set the flag if any kind of result that occurs that result in the 0 or the negative or etc, carry or whatever. So oops, I didn't execute this instruction right. So in here what happens, the value in R5, that is 0, will be added to R2. R2 contains A. So 10 plus 0 is equal to 10, that will be stored into R5. And R5 now contains 10. And this is also similar. Yeah, that stores 10 plus 7, sorry, okay. R5 contains 10, right? That will be added to 7. So 10 plus 7 is equal to 17. And if I do an SI, it will contain a value of 11. If you just convert this 11 to decimal, it will contain a value of 17. Okay, and this is all for the add instruction. In this video, we will be looking at the sub instruction. So the sub instruction is an arithmetic instruction that does subtraction. This is similar that of the add instruction we saw earlier. So it has a similar syntax. These are the sources and this is the destination. It works by subtracting the values in a register and writing the result in another register. We can see an example down below. Here R1 contains 2 and R3 contains 5 and R5 contains 0. So R5 is the destination register and R3, R1 are the sources. So here what happens is R1 is subtracted from R3, that is 2 is subtracted from 5, and that gives us a result of 3, and this 3 is written into R5. Similarly, it supports the immediate value, and here R3, sorry, 4 is subtracted from R3, and this result is written into R1. So we can look at the examples now. I can open my lab and I will log in using my credentials, and I can quit now. Just clear this and I will do an ls, and there is the sub. Yeah, this is the program, and if I do a cat and sub s, so these are our sub instructions. So we can use gdb again, and we can wait. Okay, it's done. We can put a breakpoint at the start, and I can say start, and I can run using pressing R and pressing enter. And if you look at the registers, they all have a value of 0, and there is a move instruction. I can just step into, and R0 will contain 2 and R3 will contain 7. So here what happens is R0 is subtracted from R3 and the result is returned to R3. So R0 contains 2 and R3 contains 7. So 7 minus 2 gives us 5, and this 5 is returned to R3, and I can just press enter. If I look at R3 now, R3 will contain 5 as expected. So in the next instruction, it says R2 is subtracted from R3. So R3 contains 5 and R2 contains 0. So 5 minus 0 gives us the result of 5, and that will be returned to R6. Now if we check now, R6 contains 5, and the next gives us 1 is subtracted from R6, that is R6 is 5, and 5 minus 1 gives us 4, and that will be returned to R1. And if we check R1 now, R1 contains 4. Okay, and next is a move instructions that copies the value 3 into R6. R6 now contains 5. After this instruction, R6 will become 3. So R6 is now 3, and this is a subs instruction. So this S is specified. If the S is specified, it will uh, set the flag. If any negative or 0 or anything occurs, it will set the flag. In the normal sub instruction, that is without the S, if any negative or whatever the result in the CPSR is not set, so we can check this if it works. So R6 is 3 and this is a 7, so 3 minus 7 will definitely gives us a negative number. So if we just execute this, the negative flag will be set. I can now do an SI, and it now sets the negative flag. It only sets the negative flag if this S is specified. If this was a normal sub instruction, it would have set the negative flag. I can now do an edit. I will show you what I mean now. I will use the nano and edit this instruction, and I will remove this S, and I will paste this, and press no. And if I just do a cat sub dot s, the S is removed. So I can do assemble sub dot s, and I will say sub dot o, and I will link the file, and it's done. And if I run it using GDB, we can wait. Okay, if I do a discuss on the label start, and I will say start. Okay, now this sub instruction is changed to sub instruction, so we can put a breakpoint here, and I will just put a breakpoint, and I can run it using R, and it is paused here and it says stop. So that the next instruction to be executed is this line. So in the earlier time when we executed that, the negative flag was set because this give a negative output, right? So if I do an SI now, the negative flag will not be set, because why? There is no S specified here. If the S is specified, if any CPSR status is occurred when this operation is done, it will be set. Like if this gives us a negative result, or this subtraction gives us a 0, it will set these flags. Okay, but this gave a negative number. If we check the R5 register, it says FFFF, and see it is a negative number, but it doesn't set the flag to negative. Okay, that is the difference between subs and sub. It is similar in that of add and adds. Okay, we will see in the next video. In this video, we will be looking at the MUL instruction. So the MUL instruction is an arithmetic instruction that multiplies the value in registers. It has a similar syntax that of the add and sub instruction we looked earlier. So it multiplies these values in the registers and produces the result and stores that result into the destination register. We can look at an example below. These are three registers, and R1 holding 2 and R2 holding 1 and R0 holding 2. We can look at here, it says MUL R2, R1 and R0. So R2 is the destination register, and R1 is the source 1 and R2 is the source 2. So they multiply the value in R1 and R2, that is 2 and 2, and it produces a result of 4, and this 4 is written to R2. So R2 now contains, and there is error here. Oops, I will go back and edit this error. So the destination is stored in R2, right? I will say R2, and R2 contains now the value of 4. Now we can look at an example in our lab, and I will just say ls, and we can look at yeah, this is the assembly. You can just say cat and paste this file, or I can just write it, and we can see the multiplication instruction is written down here, and we can use our GDB to look how this works. And I will run the program using GDB, and we'll wait until this loads, and we can wait. Yeah, it's done. So if I just do a discuss and I say start, you can see our instructions. They are located here, here and here. So you can put a breakpoint as we do every time, and I will just say B and start. Oops, it's not working. And B and start. So a breakpoint will be put on the first instruction, that is the move, and we can run our program using R, and our breakpoint will be hit, and in the first instruction it loads the value of 1 to R1. Initially all these registers contains the value of 0, and if I just say SI, R1 will now contain 1. So as expected, R1 contains 1, and similarly R2 will contain 4. Yes, R2 now contains 4, and here is our multiplication instruction. It multiplies the value in R2 and R1, that is 1 and 4, and 1 multiplied by 4 gives us 4, and that 4 will be written to R4, and we can check that. If I do an SI, we can just inspect R4. R4 now contains 4, and I can again do an SI. I can just press enter, and if I press enter, what we can see, that is R2 that contained the value of 4 is multiplied by R6. R6 initially contained a value of 0, so 4 multiplied by 0 gives us a value of 0, and that 0 will be written to R5. So if we check R5, R5 contains 0. So we are moving to the next instruction. R0 now contains 0, and R2 contains a value of 4. So 0 multiplied by 4 gives us 0, and that result will be stored to R1. And if I just press enter again, R0 will contain 0. So R0 is containing 0 as expected. So that's all for move instructions, and this also supports this X suffix. Okay, and bye. In this video, we'll be looking at the load store instruction. As I said before, ARM is a load store architecture. So what it means is it cannot do any direct operations on the data in the memory. For that, the data should be loaded into the registers. After that, we can do certain operations on the data that is stored in the registers and can be rewritten back to the memory. So for that, we'll be using the load store instructions. So firstly, we'll be looking at the load instruction. So load instruction loads the data from the memory to the registers. So you can look at the syntax that says LDR, the destination register, and the source. This bracket indicates this is like a pointer. So if you look at the example, var1 contains this address which points to the value 4, and after executing this instruction, LDR R1 comma bracket of variable 1, and after executing this, the content of var1, which is this memory location, will be loaded to R1, and that will be pointing the value 4. So this is what is happening. If you don't understand, this is what I meant. var1 is a variable which holds the address 0010243, which points to the value 4, and after execution R1 will contain this address. So that's all. And now we can look at the labs. If I just say ls, this is, I will copy this and I will do a cat, and it will print the code. If you look at the code here, var1 is a variable which stores the value 3, and var2 is a variable which has the value of 4, and these two are variables which hold the value 3 and 4. And if you look down below, there are other two variables which holds the address of the var1 and var2. So adr underscore var1 holds the address of this variable, that is var1, and adr underscore var2 holds the address of this variable, that is var2. And similarly, we can look here, these are our load instructions. So ldr r0 and this variable, and similarly ldr r1 and adr underscore var2. So these are two variables which holds the addresses of var1 and var2. And now if we run gdb, it will take some time, and it is loaded. we can do a disassembly of the start. And if you look at here, oops, this is, and so oops, I'm sorry, this is not the name of our program. Our program is this. It says load store 1, and I will say load store 1, and we can wait again. Yeah, and now we'll do a disassembly of the start. If you look here, it is entirely different from what we are seeing here. It says LDR and ADR underscore var1, but here it says PC, 16, and it is saying some address which is this ADR underscore var1 and ADR underscore var2. So what is this? This is called relative addressing. So it uses PC to address the different variables in our memory. So if you look here, I can say, you can close this, and I will draw something, and this is our PC, and this is our variable 1, and this is our variable 2. So PC is located in this address. I can say PC is located at this address, that is 0001 and 0000. Okay, and similarly R2 is located at this address. It says 0001 0004, and similarly R2 is located at 0001 and 0008. So if we look here, variable 1 and variable 2 are located at these addresses. In relative addressing, PC is located in a specific position, and we can access these variables using the PC by adding specific bits to it. So if you look here, variable 1 is just 4 bytes after the PC, and similarly if you look at variable 2, it's just 8 bytes ahead of the PC, right? So if you want to get the address of the var1, you can just say PC plus 4. So it's equal to 00001 plus 4, right? So this will be equal to 0001 that points to this address, right? It is the address of the variable 1. And similarly, if you want to get the address of variable 2, we can just say PC plus 8. So this is called the relative addressing. It will reduce the space used by the memory. That's why we can see here the variable name is replaced by the PC. It means the same thing, but it uses PC to relatively access the variable. So we can put a breakpoint at the start and run our program. And firstly, it says load the content of this address to R0. So our GDB is smart enough to know what this address is. So it says this position is this address, which is our ADR underscore variable 1. If I just copy this address and inspect what is the content in here, and I'll say I will use the examine command. Okay, I will use examine and in hex mode, and I will put the address of this variable, which is highlighted by our GDB, and GDB says that this address is what it is showing by here. And if I paste this here and press X, and it says the content of this location is this address which points to the value 3, and similarly we can see a relative addressing here which points to this address. Firstly, we can do an SI. After SI, this address will be loaded to R0, and I will do an SI. And if you look at R0 here, it loads this address and it is pointing to 3. And similarly, we can inspect this address as well, which says this location is equal to this address, which is our ADR underscore var2. So I will be saying examine command and I will be putting our address, and I will say, and this is our address, so it points to the value 4. If I do an SI again, R1 will hold this address which is pointing to 4. And similarly, in the next instruction, it says load the value that is referred by R0. So R0 holds this address, right? So after executing this instruction, R2 will contain 3. So in here it's not using the relative addressing, it's actually directly accessing the content in R0 and loading that content to R2. And if I do an SI here, R2 will contain the value 3. So that's all for the LDR instruction. In the next video we'll be looking at the store instruction. So bye. In this video we'll be looking at the store instruction. As I said before, our ARM is a load store architecture. So if any changes or operation is need to be done on the data in the memory, it should be loaded to the registers first, and that is done using our load instruction. And after we done the operations, we need to write the data back to the memory. This is usually done using the store instruction. So store instruction stores the data from the register to a memory location, and this is the syntax. It is different from all the syntax we seen from above videos. If you look here, this is the source and this is the destination, and we can look at the example here. Here R0 contains 3 and R1 contains a memory location. So when this instruction is executed, that is str R0 and R1, so this stores the value of 3 to the memory location which is referred by R1. So after execution, the memory location that is referred by R1, that is this location, will have the value of 3. So we can look at the lab now. I will move on to the lab. Okay, this is the program. It's already loaded. I don't want to waste any time. GDB is very slow, so I will discuss the start for you. This is exactly and this is okay. This is exactly the same program we done on the load instruction. Okay, I can put a breakpoint on the start, or I can copy this address and say B and put a pointer sign. Okay, and I will run using the R. We know how this instruction works and how the value is stored in these registers. We done that in the other videos, so I don't need to show you that again. I will just do an SI on each, and SI again and again. So all this load instruction has been executed. Now we'll be looking into a store instruction. So If we look at R2 contains a value of 3 and R1 holds a memory location of this. So it says this memory location holds a value of 4. So if we step into what will happen, the value 3 that is stored in R2 will replace these 4 in this memory location. So after final execution, this memory location will have a value of 3, and we can see here R1 has this address and pointing to 4. After execution it will point to 3. Okay, and we can do an SI, and S, the value in this memory location is now updated by the value in R2, that was 3. Okay, earlier that was 4, now it is 3. So that's all for store instruction. We will see in the next video. Bye. In this video we will be looking at the load and store instructions. We will be going right into the lab. So this is our program. We can see here this instruction and this instruction was not discussed in the earlier videos. So these instructions have a different address mode. So this is called the pre-index and this is called the post-index. So what actually happens here, if you look at here, this is a store instruction. So it stores the value in R2 to a memory location. So in here this memory location is specified by R1 plus 4. So the value in R2 will be stored at a memory location which is referred by R1 plus 4. Okay, and what this sign represent is the base register, that is the R1 which refers the memory location is incremented by 4. Okay, and similarly what happens here is this is a LDR instruction, so it loads the value in this register to R3. Okay, and the memory location of R1 is incremented by 4. So we can look that in our lab using GDB. I will say load, store and 2, and this is our program. We can wait until it loads. Okay, so let's do a disassembly. I will say disas and the label, that is our start, and we can see these are the disassembly. So I will put a breakpoint on the first instruction. I can just say break start and press R to run. So we know how this instruction works, right? So I will just do SI and SI, and I will do an SI again. So if we check the registers, R0 contains this address which points to the value 3, and R1 contains this memory location which points to the value 4. So what actually happens here is R2 contains a value of 3. This 3 will be stored to this location, that is R1 plus 2. If we check R1 has a location of this, so we can just use the examine command to print what's in R1. So this is the memory stored in R1, and that points to the value 4. So R1 contains this memory address which points to the value 4, and if I just say R1 plus 2, so R1 plus 2 is the memory location where the value of R2 will be stored. So if I just say R1 plus 2 contains this address. Okay, and the content of this address is this. So after executing this instruction, this location, that is this 200A2, will contain a value of 3 that is stored in the R3 register, and I can do an assign, and I can look at the location before, and if you look now, A2 contains the value that was stored in our register R2, that was 3. So before executing that instruction, R1 plus 2 contained this address and has a value of this. After executing this instruction, the value was replaced by our value 3 that is stored in our R2 register. So, and okay, that's all for this instruction, and we'll move on the next. So in here, this is called the pre-indexed. Okay, this is called the pre-indexed. So it says that the value stored in R2 will be stored to this location, and the value of R1 will be incremented by 4. So R1 now contains this address memory location. So after executing this instruction, it will be incremented by 4 and it will be resulted in 200A4. So firstly we will check the value in R2. R2 now contains 3, and that will be written to this location, that is R1 plus 4. Now this location contains a value 0, that is this location. If you do an SI 3, the value 3 will be stored in this location. Okay, and R1 will be also incremented by 4. And if I can do an SI, if we look here, R1 is now R4, and if I do an inspection on the location, we are seeing a different value in a different address. So why R1 plus 4 shows a different value in a different address? Because R1 is now incremented. So we are again adding R1 plus 4. So that is why it is giving a different location with a different value. So if we check before executing this instruction, R1 contained A0, and now R1 contained A4. So what actually happened here, the value in R2 was stored to R1 plus 4. Okay, so and after storing that value, R1 was also incremented by 4. So the location what we are inspecting before the execution of this instruction was this location, that was 200A4. So after executing this instruction, R1 also contains the same location, because why, this R1 was incremented by 4. So if you want to check on this location, you can just say R1, and R1 now contains 3 that was shown in this location. Okay, and you can go on to the next LDR instruction, and in this instruction the value referred by R1, that is 3, will be stored to R3, and similarly R1 will be incremented by a value of 4. So R3 now contains 0. So after execution it will be having a value of 3. Okay, so if I do an SI, R3 should contain a value of 3 as expected. So similarly R1 is incremented by 4. So if you look R1 points to a different location, that is 200A0. that shows a different value. Okay, that's all for this load and store instruction. So bye. In this video we'll be looking at the other examples of load multiple instruction and the store multiple instruction. So there are some prefix used in these instructions which says IA, IB, DA and DB. So IA is used to say increment after, and IB for increment before, and DA for decrement after, and DB for decrement before. So we'll go on to the labs. I will exit. I will clear this now and I will load the program once again in our GDB. And we can wait. So the program is loaded now and I will do a disassembly of the program. And these are our instructions. So I'll put a breakpoint here and copy this address and say breakpoint, and I'll paste this address and press enter. So the breakpoint is set. So I want to execute all these instructions until it reaches here. So I will press R now to run the program. So we can see a load multiple instruction with a prefix of IB, which stands for increment before. So if you consider this as a normal load multiple instruction, what happens here is these three registers, which is the destination registers, will be loaded with values which is referred from this register, that is the R0. So what actually happens here is R4 will be containing the value which is referred from R0, and similarly R5 will contain the value referred by R0 plus 4, and R6 will contain a value which is referred from R0 plus 8. So but in this case this is a increment after instruction. So this location will be incremented before putting these values to these registers. So what actually happens here is R4 will contain a value from R0 plus 4, and R5 will contain a value from R0 plus 8, and R6 will contain a value from R0 plus 12. So the value will be put after incrementing this address by 4. Okay, so what I mean is if we inspect R0 contains 3, so this 3 will not be put in R4. So R4 will only get the value, that is R0 plus 4, that is 4, and R5 will contain R0 plus 8, and R6 will contain R0 plus 12. So these are the values. If we execute this, R4 will contain 4, and R5 will contain 5, and R6 will contain 6. So we can do an SI, and if you check the registers, and for R4 contains 4, R5 contains 5, and R6 contains 6. So similarly there is a store multiple instruction with the same prefix, okay, increment before. So it is also similar that of the load multiple increment before. So the value from R4 is stored into a location which is referred by R1 plus 4. So it will be not loaded to R1 in the symbol STM instruction. Okay, in this case the location is incremented before putting this value. So what actually happens here is the value in R4 will be stored to a location which is referred by R1 plus 4, and similarly the value in R5 will be stored to R1 plus 8, and R6 will be stored to R1 plus 12. Okay, and I can inspect what is it, R1, let's say R1 plus 4. So it actually contains a value of 4. If I look at R4, R4 also contains a similar value, and R1 plus 8 contains 5, and R1 plus 12 contains 0. So after executing this instruction, this location will have the value from 6. These also will have the values from R4 and R5, but we wouldn't be able to see any changes because this already holds the same value from R4 and R5. Okay, and we can do an SI, and if I check R1 plus 12, it will contain the value 6, which is stored from R6. In this instruction, it says load multiple and decrement after. So after loading the values into these registers, it will decrement by 4 bytes. So firstly, the value referred by R0. So we can check what is R0 referring to. So R0 contains the value 3, will be loaded to R4. And similarly, R0 minus 4 will be loaded to R5, and R0 minus 8 will be loaded to R6. But if we execute this, we will see something different. So I can do an SI. So if we check the registers, as I said, 3 will be loaded to R4, and 2 will be loaded to R5, and 1 will be loaded to R6. But here it is just the opposite. R4 contains 1, R5 contains 2, and R6 contains 3. It is because the higher registers will hold higher values. So in here 3 is the highest value. So this value will be loaded to R6, and the next highest value after 3 is 2, that will be loaded to R5, which is a higher register than R4, and the lowest value is 1, and that will be loaded to the lowest register, that is R4. So in the next instruction we can again see a decrement before. So R4 will contain a value which is decremented before, so it will have the value from R0 minus 4, and similarly R5 will contain the value reference from R0 minus 8, and R6 will contain the value which is referenced from R0 minus 12. And we can check R0 minus 4 contains 2, and R0 minus 8 contains 1, and R0 minus 12 contains 0. So R6 and R5 and R4 is holding the value of 3, 2 and 1. Okay, and if I do an execute instruction, if I do an SI here, that actually happens. As we seen before, the highest value is 2, and that 2 will be loaded to R6. So R6 contains 2, and the second highest value after 3 is 2. So there is that, yeah, 2, and this 2 will be stored to, the highest value after that is 1, and this 1 will be stored to R5, and similarly 0 is the lowest number, it should be stored to the lowest register, that is 4. This is a store multiple decrement after instruction, which stores the value from these registers to the location referred by R2, and the location is decremented by 4 bytes. So firstly, the value from R4 is stored to the location referred by R2. So the value in R4 is 0, and that will be stored to the location referred by R2. If I just inspect R2, R2 contains 5, and after execution this location will contain 0, and after that the value in R5 will be stored to the location, that is R2 minus 4, and similarly the value from R6 is stored to R2 minus 8. So if I do an SI, we can see something different again. So I will do an SI, and if I just inspect R2, R2 contains the value 2. So if you look here, R0, R4 contains 4 and R6 contains 2, right? So how did this location, that is the first location, had a value of 2? So it is similar that of the uh, instruction we seen here. So higher values or higher registered hold higher values. So in here also higher memory addresses hold higher value. If you look here, R6 had the highest value. So if you check R6, R6 had a value of 2. So that value of 2 is stored in higher location, that is referred by R2. Then it is decremented by 4, which holds the value from R5. So R5 contains 1 and that will be stored to R2 minus 4. And similarly, the lowest value, that is 0, that was in R4, will be stored to a location that is lower than R2 minus 4, that is R2 minus 8. So after execution, R2 contains 2 from R6 and R2 minus 4 contains 1 from R5 and R2 minus 8 contains 0 from R4. So that's all for this instruction. And the last is the store multiple decrement before. So the value from R4 will be stored to a location that is less than R2, that is R2 minus 4. So the value from R4 will be stored to a location that is R2 minus 4. And if we check R4 and R5, R4 holds 0 and R5 holds 1. So the highest value here is 1. So it this location, that is R2 minus 4, wouldn't be having the value that is loaded in R4. It will be having the value from R5, which holds the higher value, that is 1. And similarly, the next, that is R2 minus 4, will be holding the value 0, that is from R4. But here already this location contains the same value from that of R4 and R5. So there should be no difference after executing it. Okay, and I will do an SI, and if I check R2 minus 4, it contains 1 as before, and similarly if I check R2 minus 8, it contains the same value as before, right? 0. Because why? This 5 and 4 contain the same value that of this location. That's why it's having the same values after execution. So that's all for increment and decrement prefix X. Okay, bye. So we can look at the labs now. I will use DDB and say load store, and I can just press tab for auto completion. Yes, this is our program, and we can wait. And I will do a disassembly at the start. So these are our load store multiple instructions. So what I'll do is I'll put a breakpoint here and I'll execute all other instructions. So I'll just paste the address and press R for running your program, and this is our first load multiple instruction. So if we look at the registers, R1 contains this memory location, and similarly R2 and R1 contains some memory location. And if we do an LDM, R0 and R5, sorry, R4 and R5, what happens here is it loads the values which is specified by R0. So if we look at R0, R0 contains this memory address. So we can examine R0. So R0 contains a value of 3. So this 3 will be loaded to R4. And similarly, R5 will contain R0 plus 4. So it will contain the value of 4. If I do an SI here, R4 will contain 3 and R5 will contain 4. So we can do an SI. So as I said, R4 contain 3 and R5 contain 4, and it is a store multiple instruction. So it will store the value from R4 and R5 to the location specified by R1 and R1 plus 4. So R1 is having this memory address and R4 is having this value 3 and R5 is holding 4. So when we execute this, R1, which is a memory location, will be having the value 3 and R1 plus 4 will be having a memory location that is 4. If I just examine R1, we can see the value in this location is 0, and if I just say R1 plus 4, it is also 0. So after execution, the value in 4 will be stored to this location, and similarly the value in R5 will be stored to this location. So 3 and 4 will be stored here, and we can do an SI. And if we look at R1 here, R1 contains 3 as expected, and we can check R1 plus 4 will contain 4. And this is also the similar load multiple instruction, but there are 3 registers, and similarly these are this also have 3 registers. So we can look R0. So if I just say R0 contains a value of 3. So after execution, 3 will be loaded to R4, and R0 plus 4 is 4, and this 4 will be loaded to R5, and similarly R0 plus 8 have a value of 5, and this 5 will be loaded to R6. So these values will be loaded to these registers, and we can do an SI, and we can check R4 and R5 and R6. So R4 contains 3 and R5 contains 4 and R6 contains 5 as expected. And similarly we can look at the store multiple instruction that has 3 registers, and R1 currently has a value of 3, and if we look at R4 and R5 and R6, they contain 3, 4 and 5. So if I just inspect R0, R0 contains 3 and R0 plus 4 contains 4 and R0 plus 8 contains 5. So after execution, these 3 and 4 will be loaded to these locations, but there will be no change because these locations already have the same value. Okay, R4 is 3 and R5 is 4 and R6 is 5. So even if we execute this, these values will be replaced with the same value. Okay, and I can do an SI, So if I just say check R1, it will be holding 3, and it will be R1 plus 4 will be holding 4, and R1 plus 8 will be holding 5. So it's the same. Okay, so that's all for load multiple instruction and the store multiple instruction. So we can look at the labs now. I will use DDB and say load store, and I can just press tab for auto completion. Yes, this is our program, and we can wait. And I will do a disassembly at the start. So these are our load store multiple instructions. So what I'll do is I'll put a breakpoint here, and I'll execute all other instructions. So I'll just paste the address and press R for running your program. And this is our first load multiple instruction. So if we look at the registers, R1 contains this memory location, and similarly R2 and R1 contains some memory location. And if we do an LDM, R0 and R5, sorry, R4 and R5, what happens here is it loads the values which is specified by R0. So if we look at R0, R0 contains this memory address. So we can examine R0. So R0 contains a value of 3. So this 3 will be loaded to R4. And similarly, R5 will contain R0 plus 4. So it will contain the value of 4. If I do an SI here, R4 will contain 3 and R5 will contain 4. So we can do an SI. So as I said, R4 contain 3 and R5 contain 4, and it is a store multiple instruction. So it will store the value from R4 and R5 to the location specified by R1 and R1 plus 4. So R1 is having this memory address, and R4 is having this value 3, and R5 is holding 4. So when we execute this, R1, which is a memory location, will be having the value 3, and R1 plus 4 will be having a memory location that is 4. If I just examine R1, we can see the value in this location is 0. And if I just say R1 plus 4, it is also 0. So after execution, the value in 4 will be stored to this location. And similarly, the value in R5 will be stored to this location. So 3 and 4 will be stored here. And we can do an SI. And if we look at R1 here, R1 contains 3 as expected, and we can check R1 plus 4 will contain 4. And this is also the similar load multiple instruction, but there are 3 registers. And similarly, these are this also have 3 registers. And so we can look R0. So if I just say R0 contains a value of 3. So after execution, 3 will be loaded to R4, and R0 plus 4 is 4, and this 4 will be loaded to R5. And similarly, R0 plus 8 have a value of 5, and this 5 will be loaded to R6. So these values will be loaded to these registers, and we can do an SI. and we can check R4 and R5 and R6. So R4 contains 3 and R5 contains 4 and R6 contains 5 as expected. And similarly, we can look at the store multiple instruction that has 3 registers, and R1 currently has a value of 3, and if we look at R4 and R5 and R6, they contain 3, 4 and 5. So if I just inspect R0, R0 contains 3 and R0 plus 4 contains 4 and R0 plus 8 contains 5. So after execution, these 3 and 4 will be loaded to these locations, but there will be no change because these locations already have the same value. Okay, R4 is 3 and R5 is 4 and R6 is 5. So even if we execute this, these values will be replaced with the same value. Okay, and I can do an SI. So if I just check R1, it will be holding 3, and it will be R1 plus 4 will be holding 4, and R1 plus 8 will be holding 5. So it's the same. Okay, so that's all for load multiple instruction and the store multiple instruction. In this video, we will be looking at another example of branching instruction. So we can go right into the labs. So the program is already loaded. This is our program, and I can do a disassembly from the start. So oops, this is not the program, and I can do an ls. So this is the program. I will run this in GDB once again. We can wait until this loads. Okay, the program is now loaded, and we can do a disassembly from the start. So if you look here, there are two move instructions which loads the value 2 to R0 and 2 to R1, and it's adding R1 to R0 and storing that result into R0. So R0 will become 4, and it's comparing 4 with 4. So 4 with 4 will set our negative flag. Okay, because 4 minus 4 will result in 0. And there is a branching instruction which says EQ. Okay, and there is another function called func1, and also there is another label which says func1. And if I just do a disassembly on func1, so these are the two instructions in func1. After that, we can see there is an add instruction, and there is also another func2, which is another label which is in direct branching. Okay, and this EQ, this instruction will be only executed. Yes, of course, that instruction will be executed, but it will only branch to the label if the 0 flag is set. Okay, that is why the EQ is used here. If the EQ is used, it will only branch to the label if the 0 flag is set. And we can start our program. We can just put a breakpoint on our start and run. And if I just si, R0 will become 2 and R1 will become 2 again, and R0 will become 4. Yes, R0 become 4, and it's comparing 4 with 4, which will set the negative flag. Okay, sorry, it will set the 0 flag. Okay, it will set the 0 flag, not the negative, it will set the 0 flag. And it says this branching is taken because the zero flag is set. It's why it's saying reason equal to z. That means our zero flag is set. And if I do an execution, we will be in this level. Okay. So if I look here, we are in this label. Okay. That says func1, and I can do an si. So we are executing instructions in this label function 1. Okay. We can now do a small edit on our program and see what will happen. And I will get out of GDB and edit our program. So before that, I need to know the name of our program. So this is the name of our program. I will copy this and edit this using nano. What I will edit is this instruction right here. So I will change add 2 to 0. So R0 will remain the same, and I need to assemble this conditional branching 2.s to cbr2.o. So the name is again wrong. I think this I is not there. Okay, and we can link it again using ld and cb2.o to cb2, and we can load this in the GDB. And we can wait. So it's loaded, and if I do a disassembly from the start, you can see the 2 is changed to 0. So when this instruction is executed, R0 will remain the same as 2 because 0 will be added to 2. That will result in 2 itself. And I can put a breakpoint in this instruction, and I will paste this, and I will run the program using R. So if you look at R0, R0 is 2, and if I do an SI, R0 will remain as 2 itself. Okay, and we can do a compare instruction here. When this instruction is executed, it will compare if R0 equal to 4. So it will be comparing 2 equal to 4. So it will result in a negative value because 4 will be subtracted from 2. So 2 minus 4 will result in minus 2, that is a negative number, and this negative flag will be set and the 0 flag will not be set. So this branch instruction, which has a prefix of EQ, will only branch to this label if the 0 flag is set. So if I do an SI, instead of the 0 flag, the negative flag is set, and here we can look closely. It says not taken. So what is not taken? This branch is not taken. So why this branch is not taken? 0 flag is not set. Okay, and if I do an SI, it will not branch to this label. It will instead go to the next instruction. And if I do an SI, we are in the start itself. Okay, we are executing the next instruction in the start, that is add 5 to R1. Okay, and if I do an SI again, we will be in the function 2. It is a direct branch, no condition is specified here, so it will directly branch to this label func2. Okay, so we are inside the function2 label. We can see here, and if I just say C, it will continue the program until the end. Okay, so that's all for this program, and it has some error, that's why it's saying segmentation fault. Okay, that's all for this example. We'll see in the next video. So we are in our labs, so I will do an ls, and this is our program. So before debugging it, I will show you the code and see. These are our two conditional execution instructions. So we can use gdb. I will just say gdb and the program's name and conditional execution. Oops, the file is not found. I think our program's name is not correct. I will copy this again and I will say file and I can paste it here. Just press enter. Yes, now the program is loaded and I will do a disassembly again to show you. Okay, everything is set and we will do a breakpoint on the start. Okay, before that I want to charge my battery a bit. So we are back, and as I set the breakpoint, let's run our program. And after executing this instruction, R0 will get the value of 2, and we can do an SI, and R0 is 2, and here we can see our compare instruction. It compares 2 with the number 3. Of course, 2 is not equal to 3, and the 3 will be subtracted from 2. So it will result in a negative number, and the negative flag will be set. You can see if the negative flag is set, when we do an SI, the negative flag is set. So if the flag is set, it will be in this bold white color. Okay, and you can see here if this instruction is executed or not. So it set the flag to negative. If the flag is set, this less than instruction will be executed. Okay, and if we execute this instruction, R0 will be added with 1, so R0 will become 3. This is our similar add instruction with this prefix. This prefix says it should only add 1 to R0 if the negative flag is set. So who set the negative flag? This compare instruction. And if I do an SI, R0 is now incremented by 1. Okay, and again we have a compare instruction which compares 3 with 3. So R0 contains 3 and it is comparing with 3, which will result in a 0 flag because these are the same values, right? It's subtracting 3 from 3 and we should set the 0 flag. And we can do an SI. So the 0 flag is set and our negative flag is disabled. So now this 1 will not be added to R0. Why? Because our negative flag is unset. It will only add 1 if the negative flag set. That's why this is called conditional execution, right? And if you do an SI, now R0 remains the same. So that's all for this video. Bye. In this video, we'll be looking on the stack and the push and pop operations. So what is stack? Stack is a data structure which is implemented to store data in a particular order. So stack is also known as a LIFO structure. So LIFO means the last element that is added to the stack will be the first one to be removed. Okay, so For example, if you had 10 books piled in the top of each other, and if you want to get the third or fourth book, you have to remove the books from the above, right? So for example, if you want to access the third book from the pile of books, and you have to remove the 7 books from the top, right? In that way you can take the third book. So in stack, the insertion and deletion happens on the same end, and there is something called the top of the stack. The top refers to the position of last element in the stack. For example, if you have 3 elements in the stack, then your top is the position of the third element. And now we'll be looking at the push and pop. So push means adding elements to the stack, and pop means removing elements from the stack. So this is the push. 1 is added to the stack, and 2 is inserted to the stack, and the inserted 2 is removed from here. So this is called the push, and this is the pop. So this is the application memory. So this is the memory allocated to our program when we run our program. Okay, so these are divided into 4 sections. So firstly, we can see the code section. So the code section contains the instructions of our program, and the static or global section contains the global variables which are initialized as constants before the main. And we can look at the stack, and stack contains the function calls, the local variables, and the return addresses, etc. And heap is a dynamic memory, and we will not be looking into that. Okay, and so push and pop operations in R. So push inserts elements to the stack, and pop removes elements from the stack. So we can look at an example. Here it says pop R3 and R4. So what actually happens here is it removes 2 values. Here there are 2 registers specified, right? So it removes 2 values from the top of the stack and copies that value through to R3 and R4. Similarly, there is a push R3 instruction which pushes or inserts the value in R3 to the top of the stack. Okay. Now we can look at simple implementation of stack, and I will open my paint. So I will try a stack and use this rectangle shape, and I can try it once more, and I will erase the top. Okay, so I will write some code here. Okay, so I will write here int main, or I can just say void main, and in void main there are 2 variables, a and b, and a has a value of 5 and b has a value of 6, and before main we will be having a function. So I will say void function, I will just say func1. Okay, and there is also 2 variables in this function, and I will say cd will have a value of 20, and I call this function here. Okay, this is a simple function. So when our program is executing and it reaches the main, and it sees 2 variables, int a and b. So if you ever thought of this, where these variables get the memory and how this memory is allocated. So this is all done with the help of the stack. Okay, so when here int a and b is initialized and they have a value of 5 and 6, this memory for these variables will be allocated from the stack. So here this certain memory region is allocated for this function main, and as we have two variables in the main, int a and int b is allocated in the stack. Okay, and the memory allocated depends on various things like its size. Integer have a 4 bytes, so there will be 8 bytes. This may or may not be accurate because there are other things stored in the stack, and this specific memory region is only allocated to this function main. So this memory region is called a stack frame. Okay, this is called a stack frame, and after allocating the space for these variables in the main, it will go to the function 1. It will call the function 1, and when we reach the function 1, there are two variables ab and cd. So another memory region will be allocated for this function func1, and there are two variables, right? That is ab and cd. So before that, firstly there will be something pushed into the stack. Can you guess that? It is the return address. So it is the return address. So return address, here is a typo. Oops, I can remove that. So what is the return address? So if you think of it like this, after executing all the instructions in this func1, it has to return to the main, right? So how will the program know the way to return to the main? It is done by using the return address. So the program will push the value of the next instruction after the function call to the stack frame of the func1. Thereby, after the execution of all the instructions in the function 1, the last return address will be popped off and it will return back to the main function. So this is done using a pop operation, and I am talking about the general case. Okay, in ARM this is done using the LR register. Stack is not used, but you guys should know why this stack is important. We can see that in our buffer overflow. Okay, and after executing all the instructions, this frame will be deleted and we will return to the main function. Okay, so that's all for the a simple implementation of the stack, and we can look at the push and pop operations now. We can now go to our labs. Okay, so we can do an labs. So this is our program. I will just copy the name and I will show you the content inside our file. So this is the code, and here is a push instruction and here is a pop instruction. So the value in R0 will be inserted into the stack, and similarly two values at the top of the stack will be popped off into these registers. And we can do it in our GDB, and I will use GDB once again. So this is the name of our program, push pop. And as always, I will do a disassembly so we can see our code again, and I will put a breakpoint at the start, and I will use R to run our program. So firstly there is a move instruction which will copy the value 2 to R0. Now R0 will become 2, and after executing this, these 2 will be pushed to our stack. Okay, so before that, where is this stack in here? If you look here, this says stack, so this is our stack and this is our top of the stack. So now this contains a value of 1. After execution, the value in R0, that is 2, will become the top of our stack. And if I do an SI, now our stack contains the value 2, and the next instruction copies 3 to R0. So R0 will become 3. And nextly there is a pop instruction. So that pop instruction will pop two values. Here there are two registers, so there will be two values will be popped off. Two values will be removed from the stack and will be copied to these registers. So after executing this, the first value at the top of the stack will be copied to R0, and the next value, that is 1, will be copied to R1, and these values will be removed from the stack, and this will become our top of the stack. If I do an SI, as expected, R0 become 2 and R1 became 1. Okay, our analysis is correct. And if I now look at the top of the stack, from the before, these values are removed and this will become the top of the stack. As expected, that became the top of our stack. So that's all for push and pop instructions. In this video, we will be looking into the functions. So what are functions? Functions are just group of statements which can perform a particular task. So in R, the branch instructions are similar to a function call that we see in C or CPP. So in the earlier videos, we used the branching instruction to branch to a label. Okay. So similarly, we are using branching statements to branch to a function. So these functions and these labels are similar things. So in ARM, the function arguments are passed through the registers R0 to R3. So if you have more than these arguments, that can be passed through the stack, and the return address is stored in the LR register, and we can see how this is implemented in R using our example in the lab. And I will just log in our lab, and this is the program we are debugging into. So the program starts at the main and have two variables A and B, which holds the value 1 and 2, and after that it is calling a function first with the arguments of A and B. Okay, and A have 1 and B have 2, so these are passed as argument to this function first. So if you look here, this is the function and it is initializing two variables C and D with the values of A and B, and C will contain 1 and B will contain 2, and after that it is calling a second function and it is passing C as the argument of this function second. So if you look at here, this is the second function and this argument is pretty much useless. Okay, we are doing nothing with this argument, and here it is initializing two variables A and B with the value 1 and 2. So that's all for this program, and there is a printf here which says hello world. So if I just execute this program, you can see the hello world printed here. Okay, and we will debug this program using our GDB. and I will load the file into the GDB. So it's loaded, and we can do a disassembly, and I will say disas and main is our label, right? If I just disas the main, we can see the disassembly in R. So as I said, the arguments are passed through the registers R0 to R3. So here are two arguments and that are passed here to R0 and R1. Okay, and it is calling this function first. And so we can put a breakpoint in the main itself. I will just say B and main. So the breakpoint is set at the main now, and we can now run the program using R. So the program is now started, and it is a first push R11 and LR. We can just do an SI, and I will do an SI again. We can do an SI again, and if you look here, it is loading the value 1 into R3, and if I just do an SI, R3 will become 1, and it is storing that value in R3 to a specific memory location. And similarly, in the next instruction, it is loading the value 2 into R3. So if you recall earlier, these were the arguments to the function first in our program, and we can do an SI, and R3 will become, R3 will become 2, and it is also storing the value in R3 to a specific memory location. And after that, it is the loading the value from this location to R0. So R0 will be having the first argument, that is 1, and if I just check R11 minus 8, it will have a value of 1. So R11 minus 8. So this memory location is having the value of 1, that is our first argument in our program. So this first argument is loaded to R0 as expected. So we can do an SI, and R0 will become 1. So in the next instruction, it is loading the value 2, and we can inspect this memory, and R11 minus 12 is 2. Okay, so it is loading the value in this memory region to the register R1, and that will be holding our second argument to the function first. Okay, so we can do an SI. So after loading the values into these registers, it is calling our function first. Okay, and we can do an SI, and so before that I missed the important thing to talk about. So I will just run this again, and resist breakpoint. Okay, and I will do a disassembly of the main, and I will put a breakpoint here. Okay, and I will copy this address, and I will just paste it here, and I will just press enter, and the breakpoint is set. If we run the program, and it has hit our first breakpoint, I will just see to continue, and now it has hit our second breakpoint. So if we look here, we are in the main, okay, and we are going into the function first with these arguments, okay. So as I said in the video of the stack, how this will come back to the main instruction after executing all this instruction in the first. So this return address will be copied to the LR register in ARM, okay. So if I just do an SI, what will happen? The address of the next instruction in main, I can do a disassembly again, and if I just look here, this is the next address after this function call, okay, this branching instruction, and this address will be loaded to the LR register. So BL stands for branch and link, and if I do an SI, what will happen? The address of the next instruction after this branching instruction, that is this address, will be copied to LR. So we can do an SI to confirm our analysis, and if I just look at LR contain B0, and if I just scroll on the top, so this is the next instruction after our branching instruction. So address of this instruction is loaded in our LR, so it points to the next instruction, that is main plus 14, and this is the instruction, right? Okay, so yeah, this is the instruction, and this is popped off using the pop instruction, and this will be popped to the PC, and this is how it will return to the main function. And we can do an SI in our first instruction of the label first. So we are inside the label first, okay. So now we are executing the instructions of this function first. So now we are inside the first function, and we can do an SI. So the value in R0 is stored in this location, and similarly the value in R1 will be stored to this location. If we check the registers R0 and R1, R0 contains 1 and R1 contains 2. So these are our arguments to this function first, okay. And we can do an SI. So the next instruction, it is loading that values to the register R3, and we can just skip these instructions, and lastly, if you look here, there is a load instruction which loads the value in this location to R0. So this is the argument to our function second, and if I do an SI, R0 contains 1, so the 1 will be argument to this function second. And if I do an SI here, the address of next instruction in first, that will be first plus 44, and I will show you by disassembling it. And first plus 44, this address will be again stored in the link register, okay. And we are inside our second function, which is called the second itself. So if you look at the PC here, PC contains, if you look at the LR here, LR contains the next instruction after the call to the function to the second function. So if we look above, this is the next instruction after the call to the second function, which is called to the second. So if you look at the address, it says 47C, and if you look at the LR, it contains the same address which is pointing to this instruction. Okay, which is this instruction. And we can discuss the second function, and there is nothing here. In this function it will just initialize two variables, okay, and they will be having the value 2 and 1. So you don't have to mind that. You have to look how these functions return to the caller. So I will put a breakpoint here and continue our execution using C. So if we look here, this is the last instruction in our function which is called to the second, and it says branch to LR. So if you look at LR contains the next instruction which was after the call to this second function. Okay, so this is the instruction, and if I do a disassembly on first, and this branch changed the execution to our function which is called the second. So we executed all the instructions inside the second, and we have to return back to this first function. So it is done by using this branch exchange LR. So the return address, which is the address to the next instruction which is here, is stored in the LR. So when we execute this instruction, we'll be back to here. Okay, and we can see that. And if I do the SI, we are inside the first function, and we can do SI again, SI again. So we are left with the last instruction in our function first. Okay, and it says pop R11 and PC. So the first two values in the stack will be popped off to R11 and PC. So this address will be popped off to R11, and similarly the next address which is pointing to this instruction in the main. So if I do a disassembly on the main, and this instruction is just the next instruction after our function call or the branching instruction to our first function. So if I do an SI here, what will happen? So this value will be removed from the stack and will be copied to R11, and similarly this value will be removed from the stack and will be copied to PC. As you know, PC holds the next instruction to be executed. If I do an SI, we will be inside the main function again. So we can do an SI. So the two values are now removed from the stack, and this will become the top of the stack. As we look here, those two values are removed, and this is now the top of the stack. And if we look at PC is pointing to this instruction. Okay, now we are in the main again. So if I do an SI, we have returned back to the main and executed the next instruction after our function call. So this is a branching instruction to our printf. So if I just say C, and it will print hello world. So that's all for function R. Okay, in this video we will be looking at the loops. So loops are used for performing repeats of a sequence of instruction until a specific condition is met. So loops are actually used for repeating something. So for example, if you want to print like 1 to 10 numbers in natural numbers, you can use loops. So it will make the process very easier. We have seen several loops like for loop and do while loop, etc. in our C or CPP, and we can look how these loops are implemented in our R. So we'll go right into the lab, and I will do a clear, and I can do an ls. So this is our program. So before loading it in our GDB, I can show you what's the source code. I will do a cat and I'll paste the name, and if you look here, the program starts in our start label and it's moving 0 to R0. So it's comparing if R0 is equal to 4, and if R0 contains 4, it will branch to the end, which will end the program. Otherwise, it will add 1 to the R0 and it will again go to the start of our loop, and we can load this in our GDB, and we can wait until this loads. So I will do a disassembly here again. Oops, the loop is actually happening in a loop level, so I'll just disassemble the loop. So if you look here, initially R0 will get a value of 0, and it's comparing if R0 is equal to 4. If 4, it will set the 0 flag. Why it will set the 0 flag? It will does a subtraction from 4 subtracted from R0, that will result in 0, and that will set a 0 flag. If the 0 flag is set, this branching instruction will branch to this label. So if we check this label will end our program. So otherwise, if R0 doesn't contain 4, it will not branch to this end label, and it will move on to the next instruction. So in this next instruction, it will add 1 to R0, and again there is a direct branching instruction. So this will again branch to this label itself, and we will be starting from the start of this loop label again. So again we will compare the value with the 4 and check if that's equal to R0, and we'll do again a branching. If the 0 flag is set, it will end the program, otherwise it's adding 1 to R0, and this will happen until R0 becomes 4, and I can put a breakpoint in our start and run our program. Now if I do an SI, R0 will have 0. Initially the registers are 0, so you don't need to set any value to it, okay? And here it's comparing R0 with 4. So if I do an SI, R0 will not be equal to 4, and the 0 flag will not be set. Instead the negative flag will be set. So this flag is not important here right now, okay? There is only this instruction, that is EQ, and it says the branching is not taken, because why? The 0 flag is not set. And if I do an SI again, we will move to the add instruction, and if I do an enter, 1 will be added to R0, and it will again go to the start of this label, that is the loop label, and will again go to the first instruction, that is this compare instruction, and it's again comparing 4 with R0, and we can do an SI, and 1 is not equal to 4, and the 0 flag is not set, so it will not branch to the end label. And we can do a step and 1 is added to r0, and we are again going to the start of the loop, and now r0 contains 2, and we can just step again, and the branching is not taken, and again r0 is incremented by 1, and again we'll go to the start of the loop. Now r0 contains 3 and it is not equal to 4, and we'll do the same process again. Okay, so if you check now, r0 is now 4, and if I do an si, it will again go to the start of the loop label, and it will compare if r0 equal to 4. Now r0 contains 4, right? And after comparing this, 4 minus 4 will give us a 0, and it will set the 0 flag. And if I do an si, so the 0 flag is set. Now it says the branching is taken. Why? The 0 flag is set. So if I do an si, we'll be inside this ending label. Okay, and hereby the program will be ended. So that's all for the loops. Bye.